a bit slow, so so anyway, so I probably in remaining time, I probably will jump to skip some pages. Okay, so so what the first thing we consider is not on yet. Okay. So now we come to a question. So this is I mentioned last time. Let's say in many cases we do have a finite time singularities. Okay. So now let's consider the case. What happens at the finite time singularity? At least at what we expect. Okay. And so you will see a few conjectures. And many of these can be verified, and some of this verified, unfortunately, using knowledge in algebraic geometry we still need to develop a geometrical method, a differential geometric method to do that. But at least we can verify this conjecture if we and on the algebraic manifolds which are better understood. Okay, so first, let's say consider what happens when the time goes to capital T when the capital T is finite. So finite time singularity is always pick up the things with positive curvature. So if you think dimension 3 case, let's pick up S2 that has positive curvature. Okay, and similar things to here too. Though we don't quite see a curvature. Positivity of curvature, but we can see a certain positivity in the first Chen class. So this is what we expect first. So you look at your solution. Omega T is a solution of Kähler Ricci flow. You have here. Okay, so there are solutions here. So you know it cannot go beyond this point. You have to go through some surgery. So what happens is the following. So first we say this M, that's an initial manifold, together with this family of metrics, converge to a metric space in a Gromov-Hausdorff topology. So it's a weak topology. It's a topology about the metric spaces. Okay. So don't worry about that. So then what the key things this is a weak topology, but in order to continue, we need to know this has a certain regularities. The first MT is a compact Kähler space, so itself may have singularities, but it's like variety things. So if algebraic, then this is just algebraic variety. Okay, so there is a holomorphic map from your original manifold onto this. Okay, MT, and this has a limit. That's I already say is established by this Zhang Zhou. There's a unique limit omega T descends to a current on the MT. So then, namely, this limit is a pullback or something from here, from MT. So okay, so and which is a smooth metric on the Zariski open set. So induce the distant function T. So namely this metric space has certain regularity. It's given by metric on the regular part. So here the MT0 means the set of regular value of this projection here. This projection here. Okay, and then we also require this convergence to be nice enough to be this in a smooth topology. Okay, smooth topology. So this actually tells you this actually, if you think recall a little bit 3-dimensional case, we don't have quite this even conjecture here. What is a model? So in the Kähler case, actually you have a kind of modeling here. Okay, even though you, as I will tell you in a moment. Okay, so this is what we can do. So if I assume the case, if this class is non in the sense non-collapsing, so it's this is a limiting Kähler class. So this is this omega t is omega 0 minus t of C1m is a cohomology class of a limit. Okay, and if this has a positive volume, and this is let me for simplicity let's assume this case. So this is a case for except when if algebraic manifold is called has a quadratic dimension minus infinity. This is always true. This assumption. So let's only consider this case. So then this converges unique smooth metric outside varieties. Okay. So actually partially can verify the previous things, and recent things what we did with Nalev and Zhenrui Zhang is may provide it's actually two different Zhang. Okay, Zhang is like Kim in Korea, so it's many Zhang. So may provide some approach to solving this conjecture once this is positive. And this last conjecture holds actually for most manifolds. So this conjecture is actually can be mostly proved. Okay, so second is hardest the conjecture that's known. We can only verify it in the case of general type when the things is when assume certain algebraic knowledges. Okay, so when we come to this point, we are m in the previous it goes to mt. Okay, so this is pi t. That's what on the previous things. So this is let's assume previously, and actually I said is we can check, and I believe we can check it. So then, but this is a singular, and you cannot quite run the Ricci flow on this. So what you do is you need to have a different resolution. Okay, and the resolution is maybe only a partial resolution. So you have another resolution, then you can continue the flow on that. So precisely this condition says this you have another resolution, and this might be singular, but it's not so bad. It's Q factorial. Maybe forget this terminology, and this is a key condition. So namely, after this, so this is a Kähler class of a pullback of omega t. It's like here, okay, and then you want to say as t bigger than capital T and small, you want this to be support some Kähler class. Okay, so this is a condition. Namely, in this process, you kill some positivity in the this is C1m, sorry, and positivity in the first Chen class, and then the C1m prime is somehow not positive in the resolution direction. So this is usually in the algebraic is a flip. Okay, so it corresponds to flip in algebraic geometry or birational algebraic geometry, and the m prime may be singular but only not terminal singularity. So this is actually analytic guarantee, and the volume form is integrable. You have a well-defined volume form. So such a things can be regarded as either blow down or flip of m. So I should say sometimes m prime could be coincide with mt. That's a blow down case, and sometimes mt is too singular. You have to find another resolution. This is called a flip. Okay, so this conjecture why I say it can be verified if you know the existence of flip, then you can check it. And also in two-dimensional case, complex two-dimensional case, this is always a blow down, and this can be verified. Okay, but in general, I don't know. Okay, so if you assume there's a flip, I can do it. And two-dimensional case we can do it. Okay, complex two-dimensional case we can do it. So even in the general in high dimensions, we hope to, for example, dimension 3, we know the existence of flips. So then there's no problem to verify this. But that's not best we hope, because in this existing flip is we need to use the knowledge of algebraic geometry. So I hope eventually, by analyzing the curvature, we can prove this analytically or differential geometrically. So this flip in terms of curvature should be a certain direction of curvature contracted, and then you want to extend in other curvature directions. Okay, but we don't have a effective method. We just have a rough idea, but we don't know how to do it at the moment. So this is so once this is both assume this and have been verified. So as I said, verified by complex surfaces, and were projected right to general type by using a known results algebraic geometry. So that's in my joint papers in the Inventionless with Jiang Song. And assuming the first two conjectures, we need to study how rich flow extends across T. And this has been done. This has been done. Okay. So once you have an existence of this, you know how to continue the flow. And this time is actually better than the three-dimensional case. We know the flow after surgery is uniquely determined by flow before the surgery. Okay. So this has some advantage of this. So then after that, maybe as quickly, so you can construct a solution with surgery, Keller-Rich flow with surgery. So let me just skip that. Okay. So and this time we construct a Keller-Rich flow surgery. The solution is unique. Okay, it's unique because the way we in the previous picture we have a clear picture, even though we cannot prove all of them. So then the next is you assume there are only finite surgeries. Okay, only finite surgeries. So when the Keller-Rich flow GT with initial metric, G0 become extinct if this after finite surgery collapse to point as before. Okay, as before. So I have seen Keller shape become extinct on the finite time on the Fallon manifold if initial Keller class is proportional to first Chern class. So this Fallon manifold, or say a manifold with possible first Chern class, corresponds to a Poincaré conjecture in the dimension 3 case. Okay. So this is also have a conjecture here. So a Keller-Rich flow become extinct at finite time if and only if underlying algebraic manifold is birational to a Fallon-like manifold. So here, so if this algebraic manifold is birational to a Fallon manifold, then this Jiang Song actually establishes this conjecture, verify this conjecture. That's a part of this conjecture. Okay. But we don't know if it's become extinct at finite time. It's the underlying manifold has to be Fallon manifold. And so here I tried this conjecture. It's been less precise. So maybe there are some interesting one can construct example or not. So I put Fallon-like. It's certainly I will in this process from what I speculate, it certainly have a lot of rational curves. But I cannot in low dimension it has to be Fallon-like by rational Fallon manifold. But whether for example complex 2 dimension is always a Fallon manifold, a rational surface. But in high dimensions, this iterative process, because this collapsing could be first collapse to low dimensional things and continue to another low dimensional things eventually to a point. But for those kind of manifold is same as birational to is birational Fallon manifold or not. I'm not sure. So this could be algebraic problem, right? So it's whether you have a manifold which is you can inductively fiberized by Fallon manifolds, but itself is not necessarily birational Fallon manifolds. Okay, so I'm not sure. So I put it this way. Okay, but anyway, in this program, what we like in the geometrization conjecture, we can say maybe the most interesting thing we will consider is not consider this. At least for most algebraic manifolds, we are not considering finite time extinct things. We consider cases when the quadratic dimension is bigger equal to 0. Then this is not the case we need to worry about. Okay, so all these things about. So so now this is answers once we have the previous things, you answers this first question, first step. Namely, we can construct the Kähler-Rich flow with surgery for all the time, including extinction time, finite extinction. Okay, so then the next is you can think is assume this exists, namely after finite surgery, and after finite manual surgery, this mn up to this, then the first Chern class of this is numerically non-positive. So then we by this by this result of with Jiang Song, actually, which extending my previous work with Zhang Zhou on the smooth case, we have a global solution. So now at this after finite surgery, you have a global solution. So then you ask this, what is the limit as t goes to infinity? So this is like in a three-dimensional case, is you after finite surgery, you want to see what's the limiting geometry is. Okay, so maybe I stop here to say a little bit, or say maybe emphasize one thing. So in the algebraic case, in this Kähler case or algebraic case, this finite time surgery is basically kills positivity in the first Chern class. Okay, so finite manual surgery is like you kill all the after finite manual surgery you kill all the positivity of this. So rich flow, if we are lucky enough, what you get is you go along the rich flow. After a certain time, you reaches the minimal model of original manifold. So by minimal model in algebraic geometry, which means you have a birational model which has whose first Chern class or whose canonical class is numerically effective. Okay, so finite time surgery is like that. As you can see, okay, in the case of complex surfaces, it's easy to see because each time we kill some cohomology class. So you can only do finite many times to do that. So complex surface case, you can check everything what I said before. And some of this verification is very simple actually. Okay. But in high dimensions, because flips is less clear. Okay. So then so after that we come to second step is we want to this omega t now under these things exists for all time. As t goes to infinity, we want to say converge to a canonical model. Okay, maybe after scanning normalizations. Okay, so here since I didn't say the dimension 3 case, let's see what emphasize here. So this step in a sense is solved. Okay, so first we observe by scanning a metric and reparameterizing a time, we can get a normalized Kähler-Rich flow. Okay, and the lambda is 0 or 1 depending on first Chern class. Okay, so it's some constant determined by first Chern class. Okay, so basically we want to keep volume bounded. So then we have a few cases. So it's so first let me recall a little bit what's the structure of this of a manifold supposed to be like. Okay, so this try to illustrate. So I do that. So the flow should be able to tell you this if you you have develop a method strong enough. Okay, so say suppose it's a smooth projective manifold, and suppose I make life simpler. I assume this has a fibration. So by a canonical class, so this is canonical model. So I assume exists some canonical model. So then you get this image of that and so on. So if m, let's drop this. Okay. So suppose I have a canonical model. So there are a few cases we know. So one is when the canonical model, dimensional canonical model is 0. So this time it's like a rich flow converges to a Calabi-Yau metric on the M as currents and the smooth topology on the regular part. So this is like in a three-dimensional case corresponds to a Euclidean space case, converge to the Euclidean space metric. Okay, only thing in the Keller case, because dimension can be higher, the picture a bit complicated. The limit might be singular things. Okay, but singularity is a smaller set. Itself is on the subvariety. So and this is general type case. So if a canonical model has the same dimension as the original manifold, it's a minimal, and of general type, one can show there is a canonical Keller-Einstein metric, and possible with singular on a small set, and furthermore normalized Ricci flow converge to these things. So this already proved, essentially proved by Suji, and we fixed some gaps in his proof. So more recently, Jiang Song actually proved that this convergence is even in the Gromov-Hausdorff, in the Cheeger-Gromov topology. So it's a bit stronger topology. I don't go into detail. So these two parts corresponds to this dimension 3 case is like this. So this we dropped out. This corresponds to a finite extinct case. We don't need to worry about the non-time existence. So the first case corresponds to this flat. This is case 1. And this is the general type, case 2. Okay. So that's so then in dimension 3 case, they are so-called degenerate cases. And also true in this case, namely that's a case we need to consider when the dimension of canonical model is between a 0 and n. Okay, this actually corresponds to this case. So that's a 5 in dimension 3. There are five geometries we in the Thurston discussed, but here we have to also find these geometries. So then this case we know this is this pi from your manifold. So let's just assume this your Mn just your original manifold to a canonical model. Okay, and then the fibers this time has a positive dimension. The fibers so fibers is a Calabi-Yau space. That can be easily checked. So then you have a holomorphic map from this M regular. M regular means it's a regular value of this pi, regular value of this projection. So into this multi-space Calabi-Yau, okay, diffeomorphic to type fibers. So then we come to a new class of metrics introduced by Johnson myself in more than 11 years ago. So this is called generalized Keller-Einstein metric, and is given by this. So if you forget about this, that's just Einstein equation. But now we need to twist it by a Princeton metric, by a changing of fibers. Okay. So same picture when in previous hour I said here the degenerate case. Actually, one can also read that in such a pictures. And write these things in this picture. Though this is probably not the way Thurston considered, but from a metric aspect, this is a uniformized way to see these degenerate things. So and then we can Johnson and prove any canonical model M infinity there's a unique solution for previous equation. So like in the Keller-Einstein case, we can solve this equation. And also there is a unique generalized Keller-Einstein metric on these any canonical models. Okay. So anyway, so this is probably repeat. There's some repetition here. And moreover, we can prove for the normalized Keller-Ricci flow converge to this canonical metric. Okay, and it's a unique generalized Keller-Einstein metric on this. So what we proved is convergence is I didn't specify topology here. I only say it's currents, but actually we did a little bit more than currents. We proved like C1 alpha convergence, and there are later works, and this Feng and Zhang, that's Zhang Zhou, and Han and Tosadi, Han was another former student, proved that convergence of this in the smooth topology if fibers are if fibers are flat. Okay, and actually just 2 days ago, Han Tosadi and had some new paper, which is they didn't quite consider rich flow case. They consider some other cases which are related to these cases. They actually removed this flatness condition. So it's possible this flatness condition can be removed. Namely, this convergence can be very smooth outside the singular values. Okay. So anyway, so this there's also in a paper about so this we already have a unique limit. The only things you can still ask further questions: how regular the limit is and how the convergence is. So there are some questions like that. So for example, this we should say in the Cheeger-Gromov topology, and this has been recently solved by Zheng Zhang and myself in the case of complex surface. So this also implies all the conjecture above for complex surfaces. Okay, so in the case of complex surfaces, is very the story is rather complete, and what's interesting here is in this work, we just posted about a few weeks ago, and so in fact the method is more interesting than a result. Okay, even the result we verify conjecture maybe 12 years old. So the method is the Perelman proved, as I mentioned, proved these finite time surgery things. The finite time surgery you only need to do finite time surgery along S2, and that's by the so-called non-collapsing things. Okay, so basically what he said, if you look at the geodesic ball along the rich flow, say of radius 1, okay, and R, say suppose curvature is bounded, then the volume of this ball, the center X of Rn, is bounded down below by some kappa. So this is non-collapsing. Okay, so that's enable him to study things at finite time. Actually, there was some young person asked me about the non-time things. So and these things conjecture is about non-time behavior. So this non-collapsing is not enough. What we need to do is we need to develop some called relative non-collapsing. So even dimension jobs, we still want to bound this in terms of volume of a bigger, say, like this relative. So this itself may goes to 0 at a time infinite. Called so we extend Perelman's these non-collapsing things to a collapsing case actually, but we have a relative comparison. So it's like Bishop-Gromov comparison. I think this will be very useful, and the proof is much more evolved than Perelman's things, and it should have more applications. And you can, it's a paper posted a few weeks ago. Okay, so this is what I want to tell you about the Keller-Rich flow case, and so any questions? Maybe I should stop to give you a little break. Okay.
May I ask some questions of some previous cases of MCY, modular of Calabi-Yau?
Yes. Here?
Yeah, previous here. So then MCY is now fixed for?
MCY is fixed. Now, maybe MCY is fixed. It's like, so let me redo it and also give you an example. And because I want to, so we take M supposed to be M, this canonical, right?
Yeah.
So suppose this dimension, this is dimension kappa, and kappa is less than n. Okay. So then these fibers, generic fibers, this is a dimension of is n minus kappa is positive. Okay. So this if it's a regular value, if x is regular value, then this is Calabi-Yau. So you just look at you regard this map this x to a Calabi-Yau represented by these fibers. Okay. So let's look at the case 1 n equal 2, for example. Okay. So then the M2 in this case, say goes to Riemann. M canonical is a Riemann surface. Okay, it's a Riemann surface. So this is a quadratic dimension 1 case. Okay, so then this is called an elliptic surface and minimum elliptic surface. Okay, so then the fibers are, what is fibers? The fibers, generic fiber is just elliptic curve. Okay, so then this what I said here is look at this sigma regular. That means the regular value of this. Okay, and then you have a map. F is a map from a moduli space of elliptic curve. That's actually just H2 minus SL to Z, the moduli. Right, the moduli of elliptic curves given by this. You can also P1 minus 3 points. So it's also it's a smooth, yes, minus 0, 1, infinity. Okay, so but look at this way. This is moduli space, and this has hyperbolic metric. So then this equation here this time is just scalar curvature, because this is one dimensional now, equal to -1 plus some pullback of some volume form here from hyperbolic ones. Maybe put some function of hyperbolic ones. This is just a potential of this hyperbolic metric here. Okay, so I mean, if the vibration is trivial, namely say suppose conformal structure doesn't change, then this is trivial. You just you don't have these things. You get just a hyperbolic metric. So but in general you do have this, and it would be interesting to study what's the kind of like a complication of these metrics, this geometry. So it's similar to this Deligne-Manford things. Okay, but that's the Deligne-Manford is just for hyperbolic case, but you can twist by these things for some meromorphic functions, because by quadrilateral elliptic all this F is classified. So then you can consider also this moduli. Dimension is same, and but you get different probably compactifications.
But sometimes you might need some base change or monodromy, because
yes. So you have some monodromy. So this only is a meromorphic map function for this. This is meromorphic, as you said, from this to P1. So you also have some around each of the singular fibers. There are some of these monodromies. Okay, so you determine this monodromy, you can solve these equations. Okay. So that's for example, if it's one singular fiber, it's multiple fibers, but reduced part is smooth, then this is just give you a conic points. Yeah. But anyways, maybe I skipped that. It's okay. So maybe emphasize. So this I think it might be interesting to see a moduli space or metric of this type, right? So and interesting enough, there's in the early 80s, and there was this famous example by Donaldson, say on an elliptic surface, if you are giving an elliptic surface, you take two smooth fibers, you do a logarithmic transformations of a multiplicity co-prime to each other, then you will get another elliptic surface, and but homomorphic to original one, but not diffeomorphic to original one. So you have different differentiable manifolds, but homomorphic to each other. But from if you run both in this case are Kähler surfaces. If you run a Kähler-Ricci flow, what's the difference in the end? Canonical model. They only differ by two conic points. And these two conic points, if you open up by changing conic angles, these moduli actually are connected to each other. So I always wonder whether there are some deeper reason behind that. Okay, but that's has not much to do with this, but just curious. That's things you get in the end. Okay, so maybe I have like 20 minutes. So I quickly I want to tell you a little bit of non-Kähler-Ricci flow case. So I'm not going to. So let me discuss a curvature flow, and this is some new curvature flow I introduced with Jeff Stritz. So he is now a professor at UC Irvine. So Hermitian manifolds. So this time I don't assume Kähler. We assume is a matrix is still locally given by Hermitian positive definite matrix, but no this condition. Maybe I already no, it's not erased. So I don't have this condition. I only have this. Only have this. That's called a Hermitian matrix. So this case is the Ricci flow definitely does not preserve these Hermitian conditions. Okay. So you need some new flows. So for that I look at the Ricci curvature. So this time called the Chen connection of Ricci curvature Chen connection, which is not really I shouldn't say Ricci, but I put a quotation mark here because this is does not measure deviation volume anymore because it's not a Navier-Civita connection, and but it has an analytic formula, and now you have a torsion. This torsion simply means it's non-Kähler. Okay, torsion being non-zero, it means non-Kähler. So it's exactly torsion is d omega there. So then you consider introduce a family of new curvature flows called Hermitian, this Hermitian matrix. Basically, you want to have this Chen-Ricci curvature and plus a quadratic function in the torsion part. So this part only depends on torsion. Okay, so this flow coincides with Kähler-Ricci flow if the initial matrix is Kähler. Otherwise, it's never be a Ricci flow. Okay, for any given Hermitian matrix, the above flow has a unique solution GT. And see. So we have some analytical theory, just like Hamilton did for Ricci flow. Let's forget about that. So there are two special cases of particular interest I want to tell you. So one case is this quadratic flow function is given by this, okay, and the other is in the sense by dual of this, okay. It's just traced differently, but it's negative. So let's call the first flow called the Puri closed flow, and second called the Hermitian Chen curvature flow. Okay. So just by some names for in order to go on. Okay. So to go on, maybe I remind you. So this is a quadratic function on the torsion. So for this, in the following, I discuss two cases. They are of particular interest because they are preserve certain special structures. That's these two quadratic functions given by these two. Okay. Let's say a little bit about the first case, the so-called Puri closed flow. So we call so this why we call the PCF. That means a Puri closed flow. So in the Hermitian case, we say a metric is Puri closed if dd bar omega is 0. Okay. So this is weaker than this condition, d omega to 0, right? D omega to 0 certainly implies this, okay? And interesting enough, this condition is always true for complex surfaces. So this is because it's a simple result of Gaussian. So the pre-close always exists on the closed Riemann surface, complex surfaces. So, for example, then the Fourier closed will provide new tool to study a class 7 surface. That is actually what our motivation was. So Jeff Shaw was a postdoc. Actually, first was a visiting student at Princeton. So I just made him to compute. So the goal is, and the motivation is whether we can find some flow which on a complex which can preserve a complex structure on a Hermitian structure on a complex surface. So anyway, let's forget all this. Is a class of that is also can pose some questions. So then we proved that if this for Fourier closed case, the corresponding Hermitian curvature flow preserve a Fourier closed condition. So namely preserve this DD bar closed condition. Okay, and in fact, what we had is we did here. I didn't follow the canonical order. So actually, this is a flow we started first. So actually, we proved that in terms of Kähler form, the flow is equivalent to this. Actually, what we did is we write down this flow and prove it's parabolic, and then compute it through a computation prove it's same as the previous version. Okay, and previous version has an advantage. You immediately see it's a parabolic flow, but for this you need to check. Okay, so and then also there are some other formulations. So for example, there is another formulation through a Bismuth connection, which is defined by this. Okay, so in case of non-Kähler manifolds, because of a torsion, there's different way of defining. There's no particular canonical connection. You choose a connection depends on what the property you use. Okay, this is actually family of connection you. But a Bismuth connection has advantage, and you will see. They actually called Bismuth connection because we use this in studying torsion, analytic torsion things. So in terms of Bismuth connection, you can also write down some rich curvature things. So then you will find the Fourier closed flow is same as this. So this is one part of rich curvature Bismuth connection. So it's very much like a rich flow now. Okay, it's very clean and turns out to be very useful. And this one, and we proved this up to certain change. We prove this is so suppose let's say this is a solution of Fourier closed flow. Then we define this 3 form. Okay. Then H is closed since it's Fourier closed. This actually is an equivalence condition. Omega is Fourier closed if and only if this 3 form is closed. Okay, so then we define this vector field, and let phi t to be its integral curve. Then we proved this is a solution of a renormalization group flow twisted with B fields. It's actually some flow physicists already studied. Okay, and so it sounded. Now I give you a recipe. You can easily go back to check this must be the case. But actually, it took us a long time to figure out this, to find this formula here. Okay, our motivation at the beginning is just want to prove Fourier closed flow is a gradient flow, just like Perelman did for rich flow. But we went through many possible functionals. It didn't work. So eventually, we relate to some no flow. Okay, but I should emphasize it's a priori unclear why the renormalizing group flow twisted with B fields preserve a Fourier closed condition. So because this original flow does not tell you how complex structure changes. Okay, so one needs to figure out how complex structure evolve along the renormalization group flow. This is our finding. Okay, this is our finding. So then applying a result, we can prove this. This is a gradient flow. Okay, because renormalization of group flow. Sorry. So renormalization group flow twisted with B fields is a gradient flow. Okay, and So basically, renormalizing group flow is a Ricci flow. Twisted by B fields, that means you put some twisting terms. Okay? You can twist it with Young mills. You can twist it with B fields. The B fields anyway, it's if you think that's some fields, okay. So it's then become a gradient flow. Maybe I drop this, okay. So basically, what we can prove is the following. You can also, for complex surfaces, you have you can extend a lot of things, and then also this flow has a nice property. I only tell you what the property of this flow instead of state many results. And so another property of this flow is it actually preserves so-called generalized scalar structures. Okay, so generalized scalar structure was the first discovered by physicists because it's come out from duality by in Gates and Hall and Rorschach in the 80s. And so they are studying of supersymmetric sigma models. Later rediscovered by Quartier. Okay, so this what is this generalized Ricci flow? If you read this paper by him, there's a lot of formulations, algebraic formulations. Now here I just like have a formulation which I understand. We can tell you quickly. So basically, this is a Hermitian manifold with two complex structures. And these two complex structures relate to each other in this way. So this is a torsion of a first complex structure. This is a form of first complex structure, and the second form of complex structure. Okay, and these two complex structures, they are both compatible with Hermitian metric here. So G is a metric, Hermitian with respect to both complex structures, and they have a torsion. It's not a Kähler metric, but they are torsion. Torsion satisfies these conditions. Okay, so in a sense, you have two probably closed conditions. Okay. And we proved, we checked, the probably closed flow preserve generalized Kähler structure after coupling with the evolution equation for this. Okay, so this provided you a way of studying generalized Kähler manifolds. So say, for example, if we have developed a method which can apply Ricci flow to classifying Kähler manifolds birationally, then maybe we can also extend that method to this case to classify all the generalized Kähler manifolds birationally. Okay, but I should say we know less here because the Kähler case is simpler than a generalized Kähler case. But we do expect the same things, which may take longer time to prove. But I believe eventually one should be able to do all of this. Okay, at least it should be no surprising in the sense is if you run the flow, our new flow, it should give you the same thing as Ricci flow did for Kähler Ricci flow, did for Kähler manifolds. So actually, there's a special case. Jeff Stritz did a lot of produced a lot of results. Which, for example, this case it's very much like Kähler Ricci flow. Okay, so there's also scalar equation and so on. So this class is called the special case general Kähler, means two complex structure commutes. Okay, and this is a case he actually simplified the flow like this. So each of these is a Ricci curvature. So Ricci curvature plus you have two complex structures. So you have a plus Ricci curvature, but you project to plus part, and you have a plus part of Ricci curvature project negative part, and for other complex structures. Okay, so project means to one part. So you can also reduce the scalar equations, but it's not about complex Monchampé. It's more interesting equations. Okay, less more interesting in the sense that less known equations. So he did things I maybe skip it. Okay, so for example, he's extended. He need to extend Evans Kurloff theory to this class of manifold to do a C2 alpha estimate. Okay, so you can look at their paper. There are also other cases, and Jeff Schiss studied. He goes further than I do now. So this he spent more time on this this generalized Kähler-Rich flow than me. Okay. So next I consider this case, and I want to discuss with due to my current student Yuri and Utinovsky, and he actually did made some computations which are very quite surprising, because he considered different flow. So he put different quadratic function, which I said before. So he found the following things. So first, let me tell you terminology. So giving any Hermitian manifold, we denote by omega to be a curvature Chern connection. We say this is a Griffiths non-negative if this for any Cassia and Ada in a holomorphic tangent vectors, we have this positivity here. Okay, so original question I give to him is maybe you can use this one of these Hermitian curvature flow to prove a following conjecture. So the conjecture is following, called generalized, or maybe this could be called generalized Franco conjecture. So Franco conjecture says the first, we'll say Franco conjecture, and he says if algebraic manifold, if M is projective, and this canonical line bundle, there's a way of define that is positive, numerically positive. So then M has to be by holomorphic to CPN. So this is proved by Mori and Xu and Yao. Mori used the algebraic method, and Xu and Yao used the differential geometric method. But of course, Xu and Yao need to assume there's a metric of a positive bisectional curvature. Condition is stronger than this. Okay, so now generalized Franco conjecture was first proved. Maybe generalized. Franco conjecture. Maybe version 1 is if your M is projective and admits a metric with a bisectional curvature non-negative, then M is locally homogeneous. Okay. So it's a symmetric space. It's locally symmetric space. So there is a generalized conjecture says if you just assume this T10 M to be numerically effective, that should be implied M is homogeneous. Okay, homogeneous. And this is only known up to dimension 3. Because basically you can classify all the manifolds. This particularly implies a fellow manifold. Let's assume C1 positive to rule out some degeneracy case. So then you can say a list and kick out all the things which is not satisfied. Okay. But in high dimensions, it's not much is known. So, and the rich flow cannot do it, because you cannot assume a curvature non-negative. Otherwise, you fall into these cases. Okay. So you have to have some different things to do it. So I asked him, maybe instead of doing this, there's a Kähler metric with these things. So you need Kähler here. You assume there's only a Hermitian metric with new Griffiths non-negative, and then prove is M is homogeneous. And the other way is actually he also, before that he already checked this if it's homogeneous manifold, you can find the metric Hermitian metric with non-negative Griffiths curvature. Okay, so at least you can characterize this Griffiths non-negativity. So then he did find it, and he first found the flow. Actually, at the beginning, the first try was a bit wrong because he used some others' work, and some others' work turns out to be wrong, and then he came back to recompute it, and in the process he found the more surprising structures. So the first result he proved is if initial metric has a Griffiths non-negativity, so does GT along this flow he had. Okay, he defined. Okay, I probably shouldn't say Chen flow. It's a Hermitian Chen flow. Okay, and moreover, if a Chen curvature is positive at one point, then it's for t is positive, then the Chen curvature is Griffiths positive everywhere. So in particular, he gave a corollary of this. I'm sorry. So this corollary is actually give a generalized version of this, stronger version of this. Namely, if you have a metric which is positive at one point, then it has to be CPN. Okay. So and moreover, he also proved a strong maximum principle analogous to that of Hamilton for rich flow. This is what I didn't expect, because it has many structures. Even we understand in the Hermitian case, because of a torsion, a lot of computations are very messy, and he can come out with something clean, very clean, and good formulation. That's surprised me. Okay, so for any t positive, the set you define this set. So this is very much like in the Ricci flow case, the one Hamilton discussed. So then he proves the invariant and the torsion twisted parallel transport. So this is given by torsion. So you have two connections naturally defined by torsion. One is by torsion, one is by dual of torsion. Of course, in the Kähler case, torsion is zero. These two just Hermitian, just given by Novichevita connections. Okay, so then these two connections are coincide with Novichevita. You back to a Hamilton's case, but this time he found this. He used these two connections, and he also proved invariance. Okay, so this is maybe I stop here. So this is and he also has some other computations and result, and I guess right now. And for example, curvature evolution, he can formulate in a way it's very much like Hamilton formulated for Ricci flow. It's he can plot things in a very clean form, and prove quite a few nice theorems. And of course, this flow is like Ricci flow case, and so next step is try to examine what the finite time singularity is, and so on. Okay, so I think I stop here. There's also symplectic curvature flow. I only have 2 pages. I show you the result. That's all. Okay, so it's thank you.